Welcome to today's paper reading. Today's paper is titled, In-Context Learning with Long Context Models, an In-Depth Exploration. This paper was published on the AR14 preprint by Amanda Bertsch and colleagues from Carnegie Mellon University and Tel Aviv University. In this study, we explored the behavior of in-context learning, ICL, at extreme scales, where the number of demonstrations approaches the size of entire training datasets. We observed that for many datasets with large label spaces, ICL performance continues to improve with hundreds or thousands of demonstrations. This contrasts with example retrieval, which shows strong performance at low context lengths but has diminishing returns with more demonstrations, and fine-tuning, which requires more data but can sometimes surpass long context ICL performance with additional data. We use this setting to examine several properties of both ICL and long context models, finding that long context ICL is less sensitive to random input shuffling, that grouping same label examples can negatively affect performance, and that performance boosts do not result from cumulative encoding gains. Our conclusion is that while long context ICL can be surprisingly effective, most of the gain comes from attending to similar examples rather than task learning. In context learning, ICL has been widely adopted due to its ease of implementation and the ability to reuse a single model across various tasks. However, most research has concentrated on short context models, which are limited by their context length. As methods for adapting language models to extreme context lengths are developed, long context ICL emerges as a potential alternative to fine-tuning. This approach, however, is not well understood, and the efficiency versus performance trade-off remains complex, especially given the high inference costs over many tokens. Figure 1 illustrates the performance increase with more demonstrations, extending far beyond the context window of the base Llama 2 model. The results are based on Fu et al. 2024 long context fine-tuned Llama 2-7B model, utilizing a context length of up to 80K tokens. This demonstrates that performance continues to improve with additional demonstrations, highlighting the effectiveness of long context models in in-context learning scenarios. In this experimental setup, we utilize 5 classification datasets: TREC, TREC Fine, NLU, Banking 77, and Clinic 150. We compare the performance of several Llama 2-7B variants adapted for long contexts, including Llama 2, Llama 2-32K, and Llama 2-80K. Additionally, we include Mistral 7BV0.2 for comparison. To ensure the models produce valid labels, we employ constrained decoding in all ICL experiments. For fine-tuning, a classification head is used to prevent invalid outputs. During evaluation, we subsample 250 examples from each test set and measure performance using accuracy and macro F1 metrics, with a focus on accuracy for clarity. Table 1 provides a summary of the 5 classification datasets used in this study, highlighting their diverse label spaces and domains. The datasets include TREC, TREC Fine, NLU, Banking 77, and Clinic 150. Each with varying numbers of labels and average demonstration lengths. This diversity allows for a comprehensive evaluation of in-context learning and fine-tuning models across different types of data. Table 2 illustrates the continuous improvement in in-context learning, ICL, performance across various datasets as the number of demonstrations increases. The table presents the highest accuracy achieved and the accuracy at the maximum data point for each model. The bold entries highlight the best performance for each specific model and dataset combination. In this section, we explore 3 common methods for utilizing a large dataset: random sampling for in-context learning, retrieval-based in-context learning, and fine-tuning. Random sampling involves using a fixed subset of the dataset, while retrieval-based methods dynamically select relevant examples for each test case. Fine-tuning, on the other hand, involves training the model on the full dataset. Our results show that scaling up in-context learning from 10 to 1,000 demonstrations can lead to significant accuracy improvements, with gains of up to 50.8 points. We also find that as the number of examples increases, the importance of carefully selecting in-context examples lessens. While retrieval-based methods initially outperform random sampling, this advantage diminishes with more examples. Finally, we compare in-context learning with fine-tuning, noting that while fine-tuning requires more data, it can reduce inference costs, making it a viable option for certain applications. Figure 2 presents a comparison of 3 in-context learning (ICL) methods: retrieval ICL, random selection ICL, and fine-tuning, across 2 representative datasets. The figure highlights that while fine-tuning occasionally surpasses ICL with a high number of demonstrations, retrieval ICL assumes access to a larger test set for drawing examples. This assumption is crucial for understanding the performance dynamics of retrieval ICL. Additional results on other datasets are detailed in Appendix C. In this section, we explore the properties of long context in-context learning, ICL, and compare them with short context ICL. We observe that the performance of long context ICL shows a monotonic increase across datasets, with the performance curve flattening out without significant drops even at higher example counts. This suggests that while computationally costly, using the full context window does not harm performance. Regarding sensitivity to example order, we find that while models exhibit some sensitivity, this effect diminishes substantially with additional context. Specifically, the percentage of labels flipped by reshuffling in 1000-shot ICL is less than half that in 10-shot ICL. Additionally, we examine the impact of label sorting, which has a minimal effect at small numbers of examples but becomes dramatic as the number of examples grows. For instance, label sorting in 1169-shot ICL decreases accuracy by 25.7 percentage points, indicating that contextualization of examples with different labels is crucial and effective over short distances in the context window. Figure 3 illustrates how the impact of randomly reordering examples in context learning, ICL, diminishes as the number of demonstrations increases. The sensitivity to example order is significantly reduced in 1000-shot ICL compared to 10-shot ICL. This suggests that with more context, the importance of the order of examples decreases. Additionally, the figure highlights that label sorting, which groups examples by label, becomes more impactful as the number of examples grows, indicating a potential adversarial effect in longer context regimes. Figure 4 illustrates the detrimental effect of sorting examples by label on the performance of Llama 2-32K in longer context regimes, using the Clinic 150 dataset. As the number of in-context examples increases, the performance penalty for label sorting also rises. Notably, in a 1169-shot in-context learning scenario, label sorting results in a significant 25.7 percentage point decrease in accuracy. This highlights the importance of contextualizing examples with different labels for effective performance, which appears to be most effective over shorter distances within the context window. Figure 5 illustrates the difference between normal and block causal attention mechanisms. In block causal attention, full attention is permitted for the example being predicted, specifically the last 2 tokens. This figure helps to understand how restricting attention to local context blocks affects the model's performance, contrasting it with the usual causal attention pattern. The study investigates the mechanism behind the improved performance of models at longer context lengths by modifying the attention pattern. Specifically, demonstrations are restricted to attending to a small block of nearby demonstrations, while the test example can attend to all demonstrations. This block attention is compared to the usual causal attention. The analysis shows that performance is significantly affected by the block size. For instance, 95% of the performance of full attention is recovered with a block size of 50 examples for banking 77 or 75 examples for Clinic 150. Additionally, sorting examples by label suggests that the performance improvement is not due to learning decision boundaries within each block but rather from retrieving more relevant examples. This supports the theory that the primary benefit of long context modeling is the ability to access more relevant examples, rather than refining task boundaries. Figure 6 illustrates the comparison between block attention and full attention mechanisms using Llama 2-32K. The graph shows that block attention nearly matches full attention performance when the block size is relatively small. Specifically, blue dots indicate block attention with varying block sizes, while red X's denote full attention over a specific number of examples. The black line represents the performance of full attention over all examples. Notably, performance rapidly improves as block size increases, reaching 95% of full attention performance with blocks of 50 examples for banking 77 and 75 examples for Clinic 150. In some cases, block attention even surpasses full attention, suggesting that the primary benefit comes from accessing more relevant examples rather than refining task boundaries. Figure 7 illustrates that even when the examples within the context are sorted by label, block attention is capable of recovering performance levels similar to those achieved by full attention under the same ordering conditions. This finding suggests that the primary performance improvement from long context modeling is likely due to the retrieval of more relevant examples in context, rather than the learning of better task boundaries. In the realm of long context models, several strategies have been developed to extend the context of language models. These include positional embedding extrapolation techniques, which allow models to handle longer sequences than they were originally trained for. Additionally, fine-tuning on long context data has been shown to enhance model performance. Other methods involve incorporating retrieval-based attention mechanisms or hierarchical merging of information. For in-context learning, ICL, methods such as parallel context windows and structured prompting have been proposed to effectively utilize positional embeddings. A hybrid approach combining ICL and linear prompting has also shown improvements in performance. When comparing ICL with fine-tuning, studies indicate that while models trained for few-shot learning can generalize to new tasks, fine-tuning generally outperforms ICL, especially when using the same number of examples. Parameter-efficient fine-tuning, PFT, has been found to generally outperform ICL in certain settings. In this study, the authors demonstrated that in context learning, ICL, with large demonstration sets is highly effective. They observed that long context ICL reduces dependence on example selection, maintains stable performance regardless of example order, and often achieves performance comparable to or better than parameter-efficient fine-tuning. The effectiveness of long context ICL is attributed to retrieval from the long context during prediction, rather than cross-attention within the large demonstration set during encoding. The authors also highlighted that our understanding of ICL is still evolving, especially as properties of ICL change with the scale of the demonstration set. Their work suggests a new paradigm of adapting the model to fit as much data in context as possible, caching and reusing the encoding of the long demonstration set. This approach offers an effective alternative to fine-tuning, trading fine-tuning time costs for increased inference time compute. As the efficiency of using very long model context lengths improves, long context ICL is expected to become a powerful tool for various tasks. Thank you for watching.